Hello, everyone, and thank you so much for attending our tech talk today. We are absolutely delighted to have our friend and colleague from MUSC, Medical University of South Carolina, Beth Wolf, to give us a talk on machine learning, a topic that is very relevant to many of our projects. But before I introduce her, please let me mention some housekeeping issues. Our next tech talk will be Jihad Obaid, also from MUSC, our colleague from there, and he discussed suicide predictability research. So please do not miss this tech talk. The education credits are available for this meeting, and we will write Lisa Maturo. You need to send an email to Lisa Maturo to get the code for the CME. So I will
have it on the next page, Claudine. But
okay. Great, and the information will be also on the slides. I will enter her email in the chat box. So again, I'm really delighted to introduce Beth. Beth is Associate Professor of Biostatistics in the Department of Public Health Sciences at MUSC, as well as Associate Director of the Methodology Core for a large NIH-funded program aiming at improving minority health in rheumatic disease. She obtained a PhD in biostatistics from MUSC. She is and has been co-investigator on numerous and a very large number of NIH grants, including the MUSC CTSA. She is also a member of our ACCEL CTR board, and she has had multiple peer-reviewed publications. She's a teacher and mentor for also numerous graduate students, so we are really honored and very excited to hear this presentation. Thank you so much, Beth.
Okay, well, thank you, Claudine, for that wonderful introduction. So as Claudine has mentioned, I'm a professor of biostatistics, and most of my research interest lies in the area of machine learning and prediction modeling, and so that was sort of the impetus for this talk. I've actually given it as part of a American Statistical Society webinar, and it was a former student who had suggested the topic. So I think it's a good topic. I think it's relevant to today's medical research and kind of where we're going in the world of biostatistics and informatics. So I want to start by so part of the reason I think about this talk is, of course, machine learning approaches themselves have continued to increase in popularity in medical applications. This is particularly true as we see the amount of data that we capture at the patient level, at the hospital level, at the county level, at the state level, etc. That just continues to increase dramatically, and so we have more and more data available to us, and the ability to process and manage and utilize that data to make determinations about how to best deliver health care is a bit cumbersome. And so machine learning methods have been proposed to kind of address this idea. And these approaches themselves do offer a lot of flexibility in modeling outcomes relative to more traditional statistical approaches that people are familiar with, and they often require fewer assumptions about the data. But one of the main hesitations that people have, and I certainly encounter this in working with clinicians when I do research with them, the hesitation that's often broached about using these different approaches is difficulty in understanding how the models are defined and how the predictors themselves relate to the outcome. So if we think about a regression model, everybody has some level of training in statistics at this point in their career and is at least somewhat familiar with how you can kind of model an outcome using a linear regression model, be it a logistic regression model or a straight-up linear regression model, and understands that then those beta coefficients in the model tell you something about the relationship between those predictors and that outcome of interest. And that gets sort of lost in machine learning, and so people are a little bit more hesitant to use them. So my goal today really is to provide an overview of some of the more popular machine learning approaches that people use to model relationships between predictors and outcomes, and then secondly to discuss some additional approaches that are available for, firstly, quantifying the relative importance of the predictors used to describe that outcome. So not quite as well defined as perhaps a beta regression coefficient from a linear regression model, but still providing you some idea of which predictors are the most important in making the determination of that outcome. And then secondly, exploring some graphical approaches for exploring the relationship between predictors and outcomes. Before we move on to that, and I'm working on getting my slides coordinated. So I was also asked to add this slide to remind those in attendance that they can receive credit for the course. And I know Claudine just mentioned that, so you can email Lisa, and then there's information on this slide I think that's helpful. I just got this slide like 5 minutes before and stuck in the presentation, so just to remind you that you can, in fact, receive credit for this. Okay. So let's start by thinking about what are the goals of machine learning. So in general, machine learning approaches focus on the idea of identifying patterns in the data so that we can take some action. So we can think about things like predicting a patient's probability of treatment success for different treatments, or we can think about identifying subsets of cancer patients to try to figure out who's more likely to respond to immunotherapy, to chemotherapy, whatever have you. And so those sorts of things. And so that said, most machine learning approaches fall into one of two classes. So there are what are called unsupervised approaches, and there are supervised approaches. So unsupervised approaches are generally used to identify some underlying substructure in the data, but no specific outcome is considered. So most of you, I'm guessing at this point, have probably seen heat maps of things like gene expression. So if we think about those sorts of things where you're seeing sort of this clustering on the, I'm going to call it an X and Y axis of the heat map, and then the color patterns for each of the individual patients or tissue samples or what have you that generated the heat map. The idea is you're looking for some substructure. How are patients clustering? So you can imagine going back to this idea of identifying subsets of cancer patients. Let's say that I'm looking at a particular type of lung cancer and I want to identify subgroups of patients within that lung cancer based on their gene expression profile. So it's doing that sort of thing. There is no particular outcome in that case. We're just trying to cluster the patients together to understand that population substructure. Now, supervised machine learning approaches are applied in cases where we have, generally where we have some set of predictors and we actually have a defined outcome. So we know what their disease outcome is, and we have this set of predictors, and we want to be able to use the predictors to say something about that outcome. So in general, we're interested in the supervised case in understanding how a set of predictors can be used to discriminate our outcome. And so again, for example, we might just want to we might want to build a prediction model, or we might be interested in identifying the subset of predictors that's most relevant in discriminating the outcome. In either case, supervised approaches assume that we have some outcome that we want to examine. And the reason I bring this up is that's the focus of what we want to do today. So today I'm focused on the idea of supervised learning approaches and using them in particular for predicting clinical outcomes. So, as I noted previously, we're going to focus on this idea of supervised machine learning methods with our goal of being able to predict some outcome based on a set of predictors. And there are numerous, many methods in the literature that have been proposed to do such things. But we're going to focus on some of the more commonly used approaches. So in particular here, I'm focusing on artificial neural networks, decision trees, ensembles of decision trees, and support vector machines. And the reason I'm focusing on these, they've been around for at least 20 years now, and they're some of the more commonly applied methods. They're publicly available in a lot of software, so you can find them in R. I believe you can find them in Stata and things like that. And so there's also, if you're interested in Python and other programming languages, they're also available in things like Python. And so that being said, we're going to my goal with these methods is first to discuss exactly how they model an outcome using a set of predictors. So exactly how are these models built with some level of mathematical detail, trying to keep it not too mathematical. But then once we have that, as I pointed out, one of the hesitations is that you sort of lose that easy to see relationship that we find with linear regression models or linear type regression models. And so I also then want to go into approaches that are out there and available, again, in publicly implemented software to, number one, quantify the importance of the individual predictors that are used in modeling the outcome, and then methods of visualizing these models, so to try to understand better how these models work. Now, again, I assume I've made this assumption so far that pretty much everybody in the audience is familiar with the idea of multivariable regression-based approaches for modeling an outcome with a set of predictors. And so, of course, These approaches are able to consider multiple predictors in a single model, and then measure the impact that those predictors have on the outcome. So we can think about the beta regression coefficients that we get out, right, and they tell us something about the magnitude of the impact of that predictor on the outcome. So as I change that predictor, what does it do to the outcome? Additionally, these models also provide a formal statistical test of association in the presence of other predictors, which is really nice. So in general, people tend to think of machine learning approaches as differing from regression, but in truth, regression models, and particularly when we're talking about multivariable models, are still machine learning approaches in that they're learning a pattern in the data. So they're basically looking for a linear pattern among the predictors to determine some outcome. The main issue is, of course, that regression-based approaches have some relatively strict assumptions that they make about the nature of the relationship between the predictors and the outcome. So barring adding some interaction terms or squared terms or cubed terms or exponential terms, you're sort of assuming a linear relationship between your predictor and your outcome. Be that either on the logit scale transformation if you're talking about logistic regression, or just in linear regression, you're talking about a linear relationship between your outcome y and your predictors x. And so the approaches that I mentioned previously, so the artificial neural networks, decision trees, ensembles, support vector machines, and many of the other what are more classically thought of as machine learning approaches, often require fewer assumptions than linear regression. So they're able to capture sort of nonlinear relationships between your predictors and your outcome without specifying them before you fit the model. And they can also often handle a large number of predictors compared to regression models. So, of course, as I pointed out earlier, and the main focus of this talk is the caveat is they're not quite as interpretable as regression models, and so it's a bit problematic. Okay. So to give some context to each of these approaches, I find it helpful to provide a specific clinical example. So in this case, as I talk about each of the approaches, I'm going to be putting it in the context of a particular example. I do a lot with rheumatology here at MUSC, and so in this case, the goal of this study was to look at treatment response in patients with lupus nephritis. So we had 280 patients on whom we had treatment response at 1 year. And so our data included our outcome, treatment response, yes, no. We also had information on their demographics and traditional clinical markers that we usually use to try to assess how likely we think they are to respond to a treatment. But we were also interested in looking at a set of urine biomarkers to see if they added any value or improved prediction. So this is the context of the data that I'm going to kind of frame everything in. Okay, so starting into our methods. And again, I talk really fast, y'all. So slow me down if you have questions. The first method we're going to talk about are artificial neural networks. So artificial neural networks themselves were modeled after the brain, hence artificial neural network, right? We can think about our brain as being a network of neurons. This was sort of the idea that people had when they developed the initial artificial neural networks. So I'm going to call them ANDs. AND models themselves consist of a set of observed input features, so you can think about those as your predictors, right? So in the example I just went through, we had sex, we had race, we had clinical markers, so double-stranded DNA, C3, C4, we had our urine biomarkers. We have a set of derived features. So derived features are things that we don't observe, but they represent some relationship between our predictors that we think then just helps us describe the outcome. And then we have a set of outcomes that we want to explain or predict. So again, in the case of our last example, it was treatment response at 1 year in our lupus nephritis patient. So did they respond? Yes, no. And finally, you have weights that connect the input layer to the derived feature to the outcomes. And this type of artificial neural network that we're going to focus on is something called a feed-forward artificial neural network. It was one of the earliest versions of these things that was developed. There are many, many great advances to neural networks since that was developed, but this is sort of where we can still visualize really well. So let's discuss a little bit more detail about how these things look. So as I pointed out earlier, we have a set of input features, and again, these are our predictors x. In this case, we're going to say we have some number of x's, x1 through xp, and then we have, you'll see these sort of the lines going, and I have a cursor, I can put my cursor on the screen. So then you have basically connections between each of your inputs to your derived features. So this is what's referred to as your hidden layer. Whoop, sorry about that. Hidden layer, and so basically you have weights going from x1 to z1 to z2 to z3 all the way down to zm, and that's true for all of your x's. And then you have weights going from your input layer, your hidden layer, to your outcomes, y1 through yk. So these are, in this case, we just have treatment response, yes, no. And these, again, would be our clinical predictors. The hidden layers are something that we're estimating as we're building the model. Okay, so we see already, from a standpoint of understanding what the model looks like, you can always represent an artificial neural network, or at least a feed-forward network as a graphical picture like this shown here. So we can always show that kind of picture. Now, talking a little bit more about how we get from x to y. So in a linear regression model, there'd be no z. We would just have weights going from x to y, and that would be our regression model, and we would build a regression model. So it's a similar idea in neural networks, but we've got this additional hidden layer. So to get from our input features, x1 through xp, to our hidden layer, we apply a function to some linear combination of our x's. So if you've seen linear regression, we can think of alpha naught as being like an intercept, and then alpha m's are like our betas that we would have in a regression model. So our z's are some linear combination, based on some linear combination of our x's, where alpha m's are how strongly that x weights each of the hidden features. And sigma is an activation function, so meaning it can be a linear function, so it could just be that activation function is the identity, and essentially zm is equal to alpha naught m plus alpha m transpose x. But we can also apply things like a sigmoid function, or radial basis function, or a sine function. So this is essentially transforming that linear combination into something else. So for those of you that are familiar with logistic regression, we do a logit transformation to y and use that for our linear combination of x's. So the sigmoid function sort of equates to that idea of a logistic function. Radial basis makes that a little more complicated and is for alternative kinds of outcomes. But essentially, we still are basing it on this idea of a linear combination of our x's. Now, the reason I'm pointing this out is these alpha m's describe sort of the line between x1 and z1 is going to be alpha m1. So it's going to describe how much weight x1 has in determining what z1 is. Okay, so keep that in mind, because this gets at the idea of how do we decide on the importance of the individual predictors in the model. Okay, so once we have our alphas going from our x's to our z's, we also need to go from our z's to our y's, and we're going to do the same kind of thing. We're going to have some variable tk that's a linear combination of our z's, and we're going to apply a second activation function. So we said we did a transformation of our linear combination of x's to get our z's. We're doing a transformation of our linear combination of our z's to get our y's. So in the case of regression artificial neural networks where our outcome is continuous, we would just use the identity link. So essentially, we would use tk to get to y. Otherwise, we use the softmax, which again relates back to the logistic regression function. So very similar. Okay, so if we think about a very simple neural network where we now have 4 predictors, we have 3 derived features, and we have 2 outcomes, we can see that we could draw this whole network out. So now I have x1 is connected to z1, z2, and z3 with weights alpha 1, 1, alpha 1, 2, and alpha 1, 3. Same thing with x2, x3, and x4. And then z1 goes to outcomes y1 and y2 weighted by beta 1, 1, and beta 1, 2. Okay, so if we look at this again, we could draw this out, and you could see what this looks like. And in theory, that gives you some kind of an idea of the impact that, say, feature x1 has on our outcomes. But you have so many weights going from x1, and then you have to go from x1 through all of the z's, you kind of lose the feel for what the impact of actual x1 is. And so we'd like to be able to think about how do we get at the information to describe something about the impact of x1 on predicting y. So we can think about this intuitively. We think, okay, well, if alpha 1, 1, alpha 1, 2, and alpha 1, 3 are all large, and then beta 1, 2, beta 1, 1, beta 1, 1, beta 1, 2, all the betas are large, then we imagine that the impact of x1 on y is large. That's a relatively good place to start. And in fact, most of the importance measures that have been developed for feed-forward neural networks are based on the idea of using these weights in some way, shape, or form. So there's 3 that I'm going to focus on today, and so I've kind of talked you through the craziness of neural networks to understand where those weights are coming from. So now you understand that alpha is the weight going from your predictor to your hidden layer, beta is the weight going from your hidden layer to your output. So the first two weights that I describe here, Garçons and connection weights, both consider all of the weights going from, okay, so if L is the predictor that we're interested in, so if this were predictor 1, so just going back one, so I'm interested in predictor 1, so this is looking at the importance of predictor 1, so you're basically summing all of the weights going from predictor 1 to your output, so alpha 1, 1, 1, 2, 1, 3, all of your betas. And then you're dividing by those sum of the weights across all of your predictors. So you're sort of normalizing your weights relative to the overall weights that you observe. And that approach is called Garçon's approach. They then normalize it so that you're essentially looking at percent of weight. Right? So we take SL and we divide it by the sum of SJ. And so essentially you have weights ranging from 0 to 100, or 1 to 100, I suppose, to describe how important the predictor is, and they're relative to one another. So the larger the weight is, the more importance we're giving you. The only difference with connection weights, A, they don't normalize, but B, they allow the sign to vary. So if we went back here, let's say that alpha 1, 1 was positive, alpha 1, 2 was negative, alpha 1, 3 was also negative, and some of your betas were positive or negative. You can imagine that the sign of this thing could change depending on the weights going from X1 into Z1 through Zm and from Z1 through Zm to your outputs. So the connection weights idea was, okay, well, we also want to take into account what direction that impact of the importance is. So not only is it strongly predictive of the outcome, it's predicting it to be more or less likely. And so connection weights was trying to allow for that to happen. The third approach is a little bit different than the first two. So in the first two, right, we accounted for the weights going from the predictors to the hidden layer and from the hidden layer to the output. The group that developed most squares said, we don't really care about the weights going from the hidden layer to the output. We mostly care about the weights going to the input, from the input to the hidden layer. And not only that, they said, okay, by the way, in developing a neural network, you have to do an iterative process. You initialize the weights at the beginning, and then you use something called backpropagation to find what the weights actually are. So when you initialize the weights for all of the predictors, they're very small. The idea of the most squares is if a predictor is important, those weights are going to stop being small. They're going to become larger and larger and larger. And so they look at the difference between the initial weight going from the ELF predictor all the way through versus its final weight. And the larger that difference is, the more importance we believe that it has, because the backpropagation suggested that that one needed more weight in determining the outcome. Okay, so it's a little bit different. Now, let's look at what these things actually look like. So they can be displayed graphically, and they give you slightly different answers to some degree. So this is applied to the Lupus Nephritis data set. And so here we have our Garçons and our connection weights. So remember, these are both using the weights going from the input layer to the derived layer to the output. Garçons takes the absolute value, and so all of them are positive and they're scaled. Connection weights allows them to account for the fact that some things are negative. So this would suggest that urine protein to creatinine ratio, interleukin-2 receptor alpha, and estimated glomerular filtration rate are all very important, but these two sort of make you, the higher they are, the more likely you are to have treatment response. This suggests that the higher this is, the worse your treatment response. And you kind of lose that interpretation in Garçons. Right, so Garçon still says sort of similar things. It says urine protein to creatinine and IL-2R alpha are the most important predictors, which kind of goes with these two here, but doesn't account for whether the directionality of that relationship. And most squares, again, only accounts for how much the weights change. And what you'll notice, and it's kind of hard to see, and I apologize for the tiny, tiny writing on the x-axis, it still ranks IL-2R alpha relatively high, but it ranks IL-8, so interleukin-8 relatively high, whereas if we compare that to the other two, so here's interleukin-8, here's interleukin-8, it's saying that's the most important predictor. So it's seeing the biggest change in terms of the weights going from interleukin alpha to that hidden layer. Which one's best? There are comparisons in the literature about this, and essentially it sort of depends on your data, so I will give you that caveat. Now, Those importance measures are helpful in understanding the relative importance of a particular predictor and on how it influences the prediction of the outcome. But they don't provide a good picture of how changing the outcome changes your prediction. And so the other thing that people have developed is something called a Leck profile plot. And so in a Leck profile plot, we want to look at the impact of an individual predictor by allowing it to vary, but we fix all of the other predictors. So if we think about our data set, so we had a couple of demographic variables, we had 4 or 5 clinical variables, and we had 4 urine markers. And so you can imagine if I want to know, in this case, the impact of age, C4 complement, double-stranded DNA autoantibody, EGFR, so on and so forth, I can fix the value of the other predictors at some set value, and then I can vary age, or C4C, or double-stranded DNA, and see how my predicted response changes. So in this case, this is looking at me changing age and what happens to my predicted probability of treatment response with age, with C4C, with double-stranded DNA. The 1, 2, and 3 here represent the 20th the other predictors fixed at their 20th percentile, their 50th percentile, or their 70th percentile. So seeing sort of giving you an idea of does that relationship change as you change the other predictor values a little bit. One really nice thing about the Leck plots is they do give you some level of indication of whether or not, so like age, it's a pretty linear relationship. Same thing with C4, but it looks like if we look at EGFR, perhaps there's a little nonlinearity there. IL-6 and IL-8, there's some nonlinearity there, and same thing with urine protein and creatinine. So it does kind of give you this visual of how the predictors influence your outcome. Again, the caveat is you have to fix everybody else at some set value, but the same thing would be true for a regression model. Okay, so a few caveats with artificial neural networks. So I presented to you 3 different importance measures and the idea of the Leck plots. There are many, many, many importance measures that have been reported in the literature for feed-forward neural networks in particular, and generally with one hidden layer. So in general, that most of them are based on weight-based measures, kind of like what we've shown. There is one out there that's based on the partial derivative of the weights to the output with respect to the input. And then there's a variable selection and ranking method. So we haven't talked at all about doing variable selection. The other caveat is some of these measures, in fact, most of them are only vetted for artificial neural networks with a single hidden layer. So there are what are called deep neural networks that have multiple hidden layers, and these approaches have not been vetted for those deep neural networks that are becoming more and more popular. Similarly, convolutional neural networks, which are good for imaging data, natural language processing data, which Dr. Obaid may be talking to you about next Tech Talk, I'm not sure, don't really have these approaches available for them. And then finally, the last caveat, which I made the point about with the Leck plot, is I have to fix all of the other features at a particular value and then vary the one predictor. And so you only know how that predictor is doing at that one fixed value. Okay, so moving on from there, we can look at tree-based methods as well. And tree-based methods were popular in clinical settings because they're relatively easy to interpret. So they are non-parametric or semi-parametric methods, and the really nice thing about them is they are a graphical model. The graphical model, when they're presented that way, they're relatively easy to interpret, especially compared to many of the machine learning models. And so they're also often cited as being similar to how a clinician thinks. So you kind of make, if this is true and this is true and this is true, then I think this outcome is going to be true. And so you can see that very easily from the graphical representation. And so they had a lot of popularity for that reason. There are lots of them out there and available. We're going to talk about classification regression trees, or CART in particular, but I show some other possibilities here. There's methods called C45, C50, Quest, Cruise, Guide, so on and so forth. So there's lots of other decision tree methods that you can use. But again, we're going to focus on CART. So the main idea in CART is, and this is a very technical way to say this, is to divide your feature space into disjoint regions and fit a simple model to each region. So we'll see what this looks like in a minute. And in the case of classification, then what we do is within each of those disjoint regions that we're talking about, essentially the class that's the most frequent is the class that we predict in that region. For regression, the mean in that region is what we predict in that region. Okay, so let's look at a simple example. So these are my data over here on the right, and as you can see, I have blue classes and I have red classes. We can see that perhaps, and we have 2 predictors, x1 and x2. we can see perhaps a linear logistic regression model might not do so well. But if we think about a cart would simply make splits. So like here's our first split. We split x2 at -1. That's this green line here. And if you're below the green line, so if you're less than -1, we predict you to be in the blue class. All these points are blue. And then we go to the right. So going to the right is everything above x2 equals -1. So it makes a second split at this purple line for x1 less than 3.9. And if you're less than 3.9, we predict you to be red, and otherwise we're still not sure because you have between the green and the purple on the right-hand side, you have 3 blues and 4 reds. So we split again on x1 at 5.45, and if you're to the left, we predict you to be blue because now you're above the green, you're to the right of the purple and to the left of the blue. There's only 2 blue points there, we predict you to be blue, and so on and so forth. So essentially, you see, we can take this space in a relatively simple way. We can figure out how to interpret it, and we get perfect classification. So, in theory. Okay, so now you kind of understand the idea of this. Again, if y were a continuous outcome, we'd be looking at the mean in each of these regions to get what your prediction was. But in this case, classification is a little bit easier to wrap your head around. Okay. So to develop a cart tree, we had this cart tree, right? So we split on x1 and x2 a couple of times. The way that it's going to do this is going to use something called the recursive partitioning algorithm. So we start at the very top with all of our data, and we consider all possible splits for each of our predictors in our data set. So in our last example, we just had x1 and x2. So we would consider every value of x1 that we observed and every value of x2 and consider a cut point, like these splits shown here. And we would pick the predictor and the cut point that gave us the best separation of the data. So essentially, we're trying to make the data increasingly pure classes, increasingly more similar means, or different means between the two classes. That divides the data into 2 subsets, as we kind of described before. For each subset, that we do that again. And so we basically repeat that process until we achieve some desired level of purity. So in the last example, I would achieve perfect purity. So I had perfect class prediction in each of my regions that I was now defining. But in general, we don't want to fit to perfection because then we've overfit. So how do we get at variable importance? So again, the visual of cart is really, really nice and does kind of give us an idea of how the predictors relate to the outcome. Right? So we can have that lovely graphical tree picture that we can use. But we'd still like to be able to say something about the relative importance of the predictors compared to one another. So the first thing we need to understand is, as cart is doing this recursive partitioning, as it's picking its splits, it also does something called defining a surrogate split. So at each node in the tree, so at each point it's making a split in the tree, it groups the other predictors by, so if it splits at xj less than c, it groups all the other predictors by xj less than c or xj greater than c, and then it ranks all predictors that aren't xj. So if we're talking about x2, it'll rank x1, x3, x4, x5, x6 relative to how well they dichotomize xj. And then it picks the best surrogate split to decide the branch that's missing a value xj might belong to. Now the reason that's important is when we look at variable importance in cart, it starts by summing a goodness of fit measure. So if we think about a classification tree, it's how well are we classifying? So what's our misclassification error on either side of the split? If we're thinking about regression, we could think about like mean square error. So if I have group 1 and group 2, what is the mean square error in groups 1 and group 2? And so you're summing the goodness of fit measure for all of our observations across all nodes in the tree that split on xj. So just real quick to go back. So like this tree split twice on x2, twice on x1. So it would consider those 2 splits in terms of summing this goodness of fit measure. The reason I mentioned the surrogate splits, it's also going to account for the surrogate splits in that sum. So it's going to include this sum adjusted by the goodness of fit measure for each surrogate split. So even if a predictor isn't included in a cart model, it still gives back a variable importance measure. Okay, so just to look at what this looks like in the context of our example. Again, so this is our cart tree for our lupus nephritis example. This is done in I think it's the party package in R, and party makes a really pretty tree. So colors kind of tell you the more green they are, they're ones, the more blue they are, they're zeros. So ones are our treatment responders, zeros are our non-responders. It tells you what percentage of the data are in each split. So we start with 100% of the data. We split on IL2R alpha. And then that's 89% of our data goes to the left, 11% goes to the right, then the right splits on EGFR. And it tells you at the bottom as you're fitting them what percent of the data falls in each of your nodes and what the predicted class is. So this is a 0, a 0, a 0, a 0, so non-responders. Responder, 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 so on and so forth, and how many of the data fall in each of those nodes. And then in terms of the importance, you can get a similar plot to what we saw for the neural networks. So it gives you a relative ranking of the importance based on that improvement in performance with each split on IL2R alpha, which I think it only splits on it once. This tree only splits on things once. Oh no, EGFR split on twice. Then EGFR, then your protein and creatinine, so on and so forth. But again, going back to the idea of surrogate splits, you notice that race is never included in this model, and yet there is a variable importance ranking for race. Same thing is true for IL-6. So those surrogate splits play a role in allowing you to say how important a predictor is, even if the model itself doesn't incorporate that predictor directly into the tree. Now, there are a lot of caveats with CART. So the really nice thing, and the reason clinicians tend to like them, they are intuitive and easy to understand, but the main caveat is they don't tend to generalize well. So they tend to overfit the data. So they do, like going back to that very first example I showed you where I had perfectly classified blue and red classes, I probably overfit those data. And what that means is if I make very small changes in the data, I can get A, very different models. B, when I go to make predictions on new patients, I don't tend to do that well. And so people moved away from decision tree methods into what I'm going to refer to as an ensemble classifier. So this was the most notable improvement to CART. And so essentially the idea of an ensemble model is I'm going to build a bunch of these CART trees, or whatever decision tree I want to use, or in fact whatever model I want to use. But I build a bunch of models and I allow each model to make a prediction, and then I aggregate my prediction across all of the models that I've built. Now you might be saying to yourself, okay, well if you build a model on the same data over and over again, really are you improving anything? So what we do in ensemble learners is we do something to modify the data between each CART tree that we fit. And so that's kind of what we're going to get into. We're going to talk about two main approaches. So there's three main approaches that have been described in the literature. One of them is a combination of two of them. So we're actually going to talk about two approaches. The first approach is called boosting. So this sequentially applies a weak classification algorithm, in this case CART, to repeatedly modified versions of the training data by using a weighted set of classifiers. So what it's going to do, and we'll see this in a minute, essentially as I build the classifier, it's going to add weights to the observations, and those observations that are poorly predicted, it's going to upweight them for the next classifier. So when I build the next CART tree, they have more weight, so I do a better job of predicting them, and I go through the algorithm as I build these trees. The second approach that was suggested is something called bagging or bootstrap aggregating. So in this case, we draw bootstrap samples of the data. So we draw repeated samples of the data with replacement so that we can build a model from slightly different data sets and get this collection of CART trees that way. The third method that's selected, and this is the one that's combined with other methods, is randomization. It isn't typically applied by itself, but in this case, we randomly select a subset of predictors from which to construct our classifier. So if you think about talking about when I was talking about building the CART trees, you have P predictors. We consider all P predictors and all splits on all P predictors, and we pick the best one. So in randomization, we say, well, we're only going to consider, if we had 20 predictors, we're only going to consider 5 of those at any given split. And that's what we'll see when we look at the method that uses randomization. Okay. So to build a boosted set of CART trees, the first algorithm that was introduced to do boosting using CART trees was something called AdaBoost. And the basic algorithm is shown here. Again, sorry for the being so mathy, but it's important in terms of things like the weights. So again, it's going to do this capital M times, and M is usually something like 100 or 500. So GM of X we can think of as our CART tree. So we're fitting our classifier GM of X, which is our CART tree, to some training data using dates WI. So we initialize our observation weights at the beginning. So if I have 50 observations, a weight of each observation is 1 over 50. 150, they each are weighted equally at the beginning. So for classifier 1, they have equal weights. We compute the error of our classifier. So this is an indicator that what we observe does not equal what we predict times the weight at that particular iteration divided by the total sum of weights. We then compute a classifier-specific weight alpha m based on the log of 1 minus the error that we calculated in step B over the error, and then we use that to update our weights, right? So essentially, for observations that are poorly predicted at the mth iteration, they're going to be upweighted in the next iteration. Those that are correctly predicted are going to be downweighted. And the idea being, so if you have data that are a subject that's particularly difficult to predict, eventually there's going to be a classifier that does a good job of predicting them. And then basically so we talked about this idea of aggregation. So we are aggregating across all the trees that we build, but they're weighted by this tree-specific weight alpha m that we calculate. So if a tree doesn't do a very good job of predicting, it's going to be weighted poorly. If it does well, it's going to be weighted high. Okay, so we've got this idea now of how we construct this thing. So how do we get at the importance of the individual predictors? So we start by calculating the squared importance of a single tree. So in this case, we have something called D-K, which is the improvement in error by making the K split on the jth predictor. So again, if we were talking about age being our predictor, so we have multiple nodes within a particular tree that split on age, and basically we're looking at how well do we improve our prediction by splitting on age at those different nodes. And we sum that across all of the splits for that particular predictor in the tree. And then we average that across the M trees to get the importance for predictor J. Okay, so it's a lot like CART. Now, the reason I'm showing you two trees, in the case of the boosted model for our treatment response in lupus nephritis, I think I built 100 trees. I'm just showing you two different trees. I can't remember, this is the first iteration, this may be this is like the 35th iteration or something like that. So it's much later in the building process. And you can see, so both have 100% of the data, but this is saying that 11% of the data are class 0. This is saying that 35% of the data are class 0, and that's because of the weighting, how the observations are weighted. You also see that the trees split on different things. So this first tree splits on urine protein to creatinine. If we go to the left, followed by IL-2R alpha, followed by age. This one splits on EGFR and then doesn't split again on the left-hand side. On the right-hand side, it splits multiple times on EGFR. Also splits on IL-2R alpha and then on C4 complement. In terms of ranking, so we are seeing some consistency. So IL-2R alpha is still relatively highly ranked. EGFR is relatively highly ranked. This one is ranking age and IL-8 higher than I think we saw with the CART tree. There is some consistency across the algorithms. And we see that double-stranded DNA arrays are not at all weighted all that highly. So again, you can look at this in very similar ways to how you looked at neural networks, to how you looked at CART. Okay, now, that's how we use boosting. So remember, boosting was reiteratively reweighting the observations based on how poorly or how well they were fit by the previous classifier. Random forest uses the other two ensemble approaches that we talked about. So we talked about the idea of that bootstrap aggregating, where we draw repeated bootstrap samples from the data. And we talked about randomization, where we pick a random subset of predictors from which to choose our best predictor and best split. So random forest combines those two ideas. And it turns out that it usually has better performance compared to its single model counterpart. And it has better computational speed relative to boosting or just bagging by itself. It also generates something called an out-of-bag data set, which is we're going to see is very useful for looking at variable importance. So that out-of-bag data, when I draw a bootstrap sample, so if I have 100 observations and I draw a bootstrap sample, about 67% of the observations are going to be included in the bootstrap sample, and about 33% are going to be left out. So the 33% that aren't in that bootstrap sample are what are referred to as the out-of-bag data. We're going to use those. So if you know anything about splitting data into test and training sets, it's like you now have an independent training set and test set on which to build your model and evaluate your model. Okay, so just to run through the algorithm for random forest. So we have our data W that has response Y and a set of predictors X. We're going to draw capital B bootstrap samples, and then basically for each bootstrap sample, we're going to build a CART model, so our classifier GBX on our data. But how this is going to differ from CART. So in the case of AdaBoost, we had these weights that went in with the observations, but we didn't mess with how the CART algorithm worked, right? So the CART algorithm was just applied to weighted data and essentially still considered all predictors at each split and built the best tree possible. In the case of random forest, rather than considering, we're going to incorporate that randomization. So for that bootstrap sample, we're now going to build a CART tree, but at each split in the tree, we're only going to consider a subset of the predictors that are randomly selected on which to choose that split. So if we had 100 predictors, it's going to consider 10. And that's something that you specify, but just an aside. So we randomly select a subset of predictors from among our P predictors. We determine the best split from among that subset, and we grow our CART tree basically until it fits perfectly. And then we take our response for classification as the average predicted response across all of the trees. Okay, so as I mentioned earlier, for each bootstrap sample that we draw, we now have this independent out-of-bag data set that we've got. So for each classifier GBX that we build, we have this out-of-bag data, and we can use that to do two things. One, we can estimate an out-of-bag error rate. So as I pointed out earlier, about a third of the data are left out of any given bootstrap sample. So about a third of the data are bootstrap samples. So each observation is included in about a third of the out-of-bag data sets. And so we can estimate for each tree for which the ith observation was not included in the data used to build the tree, we can make a prediction on it and get an error rate. And it's like having an internal test and training set so that we can evaluate how well our model is predicting. So we can get an out-of-bag error rate for our tree to figure out how well our random forest model is doing. But the other thing we can use it for, so we have this out-of-bag error that we estimate. We can also use this to get at the idea of variable importance. So in random forest, the original method proposed for getting at variable importance was something called the permutation-based approach. So we take predictor xj, we disrupt the ordering. So we take it and we randomly reorder it so that any relationship that it had with our outcome is now disrupted. And then we look at the prediction, the out-of-bag error rate before and after we permute. And the larger that difference across the trees, the more importance we believe that predictor has. And though you could represent it like we represented the models for Garçons and everything else, the random forest package itself actually returns plots that look like this. So if you kind of tip these over on their side and made them bar plots as opposed to line plots, it would look the same. But basically, the larger you are in terms of either your mean decrease in accuracy or a mean decrease in something called Gini index, the more important you are. We're going to skip proximity measure because I just realized what time it is. Okay, some caveats about ensembles. As I've said, they're useful for improving the performance of CART or other classification regression tree approaches. But it has been noted that random forest importance measures have bias. So if you have continuous predictors versus categorical predictors, it tends to favor and place more importance on continuous predictors. There are fixes that have been proposed in the literature that are out there. I would also say, looking at the boosting approach, there's less evaluation that I've seen for boosting and their importance measures compared to random forest. So random forest seems to be where people go. We don't have a lot of time for support vector machines. I will get through what I can. Okay, so the last one I wanted to talk about, and I'll try to keep it short, is support vector machines. Support vector machines are probably the most black box of the methods, but they are essentially a generalization of the idea of a linear decision boundary. So just looking at this example on the right here, I have my red class and I have my blue class, and I can see that I could draw a line using X that would be defined by X1 and X2 that would discriminate between my red and blue class pretty well. And that's what's known as a linear hyperplane. Okay, so support vector machines allow us to make that a little less stringent. It turns out they're scalable for multidimensional data. So if I had way more predictors than just 2, they scale well for that. They're also unaffected by local minima. So main components are that separating hyperplane that we just talked about, a margin that defines the hyperplane, so it's sort of how far are points that are the correct class from that hyperplane, something called a soft margin and something called a kernel function. So just to go back to our idea of the linear separating hyperplane, if we defined our classes, if we were talking about a 2-class case and defined our classes as +1 and -1, we can imagine that we could construct a linear line, so we could fit a regression model and solve for where beta naught plus x beta equaled 0, and that would give us this lovely line right here. And to choose that best hyperplane, we would basically define a margin, so this green dashed line here defines our margin, and the margin is defined as basically the maximum distance of each point of the correct class from that line defined by this classifier. So we have this line. These are now, so this blue point here is equidistant from this line relative to the red points. And so our margin is then that difference between D minus and D plus. So our margin is here, and that tells us how well we're doing. And we want to make that as wide as possible. So basically separating our classes as much as possible. Now in reality, data are not often linearly separable. So just looking at this example here, and you could still perfectly separate these data, but we see that there's this line here, and this blue dot falls on the wrong side of the line. We have our margin, this blue dot falls within the line. And so the idea of not being linearly separable, we relax this using something called the soft margin. So essentially we have our margin that we define, but we're allowing variables to be on the wrong side of the margin. And how far they are on the wrong side of the margin tells us is something called the slack variable. So all those, there's my predictor. All those variables that fall between, on the right, within the margin, but on the right side of the decision boundary, have a slack variable value less than 1. Those that are on the wrong side have value greater than 1 and don't have any influence on the prediction. These points that are on the hyperplane or on the margin are what are defined as support vectors, and they're actually what are used to define where that hyperplane is. The other point that needs to be made with support vector machines is they also relax the assumption of linearity. So just looking at a simple example here. So imagine we had these data. So my outcome is red or green, so I have two classes, and I only observe this predictor X. We can see clearly there's a distinction between the red and green classes. I could draw a line here, and that would define the classes. But there's no linear classifier that can do that. However, if I take X and I square it, in the right picture here, we see that now we can actually define a line, a hyperplane, that discriminates between my red and green classes. And so by projecting our data into higher or lower dimensional space, so taking X and making it X squared, I can discriminate between the red and green classes. And so support vector machines do this to a much higher degree using transformations. So they can use polynomial transformations like an X squared, but they can also use what's called the radial basis expansion. So basically projecting the data into higher dimensional space so you get to where you have a linear separating boundary. When you observe what you get back from a support vector machine, that's projected back down into the space that you observe it in, so it looks nonlinear. Boy, we're going to skip all of this. So this goes into how you fit a support vector machine. The main point that I want to make is it uses quadratic programming to solve a convex optimization problem and something called a Lagrange function. So the Lagrange function is shown here. The main reason I'm pointing this out is here's our response, here's our predictor. So we have a response time times a linear combination of our predictors. And this alpha I defines those support vectors. So those things that define the margin, defining the boundary between the two classes. And this alpha I is a weight for each of the support vectors that we're going to use. So the data points that define that margin of the boundary. And that the only reason I'm pointing this out is that's the thing that we then go on to use to be able to define the importance, or be able to define something about the relative variable importance in support vector machines. So the final solution looks like this here. So we have this intercept term, but you see now that only alpha I, so that weight that I was showing you on the prior page, actually lends any credence to how important a particular predictor is. And it does this now. The only approach, I'm losing my set. The only approach that's available that I know of in the literature right now for support vector machines is something called recursive feature elimination. So essentially, we fit our support vector machine with all of our features, and then we're going to calculate the rank and the support weight. So that alpha I times the yi times x. So that's the reason I was pointing out what the alpha I was. It's that weight on the support vectors in terms of how they're defining that linear decision boundary. And it's a lot like a beta coefficient, but in a nonlinear way. And essentially, so we calculate this across all of our predictors, and then we remove the predictor with the lowest rank. And we do that iteratively until we end up with just a single predictor. So unlike all of the other weights that we've seen. All the other weights are relative to one another and use something about the model, how well the model predicts, the weights going, like in neural networks, the weights going from the input to the hidden layer to the output. This is just, you were removed first, you were removed second, you were removed third, and so the weights are based on how they were removed, and so they are numeric, ranging from 1 to however many predictors you have. With, if you were removed first, you have the worst weight. If you were removed last, you have the best weight. Now, there are some visualization approaches that you can look at as well. So just looking at our lupus nephritis model, here we see we had 10 predictors, so EGFR was the last one to be removed. It has a weight of 10. IL-2R alpha was the second to last to be removed and has a weight of 9, so on and so forth. So not quite as quantitative as the other approaches. Now, we can do something like a LEC plot. So remember the LEC plots back when we talked about neural networks, you were looking at basically fixing all of the predictors at a value and then varying one of the predictors. So this is setting all of the predictors at their median, I think, and then varying age, or setting all predictors except urine protein to creatinine at their median and varying urine protein to creatinine. It also, again, gives you an idea of the relationship between the probability of being a treatment responder versus not, as you vary the predictor values, keeping everything else constant. Now, a lot of the literature around support vector machines and visualization also provides ways to plot two-dimensional plots. So this is now looking at age versus urine protein creatinine and showing you what the support vector boundary decision boundaries look like. So pink is one class and blue is another class, and this is urine protein creatinine and age. And again, having to still set a particular value and then showing you what instances are red and what instances are black. I personally don't think these are all that helpful, but they look interesting. This is a slightly nicer version, which gives you sort of a density plot of, so you're most likely to be of the blue class as you get darker blue, and so these are actually pretty questionable. This model didn't do all that well. But again, looking at IL-2R alpha by EGFR, at varying levels of age, so this is then IL-2R alpha by age, varying levels of EGFR. So kind of looking at what happens for 3 predictors. Okay, and just to tie it all together, so these are the most black box methods that we've discussed, and unlike the other approaches that we've talked about, they don't really, that sort of importance measure is not all that quantitative. It's just a rank of how you were removed from the model. So again, the fact that it's doing this sort of iterative removal of features, it's conditional on the features that are in the model at the time. So it has lots of issues. If we compare the methods, we do see that they don't necessarily yield consistent ranks. So IL-2R alpha was the most consistently ranked. It was ranked 1 or 2 for everything except the AdaBoost model. EGFR also ranked relatively high for most of the models, but you can see there's a lot of fluctuation. In part, this is due to the fact that the models evaluate the outcomes in different ways, like the way that the model's actually constructed is different, and so they pick up different aspects of the relationship. The literature, it's very data dependent as to which one's going to give you the best answer, unfortunately. The other caveat, all of the models require tuning. So whether you're doing CART or artificial neural networks or random forest or support vector machines, there are tuning parameters that you have to tune prior to fitting the model. And if you fail to tune the model, you can get very poor fit and feature importance measures. So this is my tuned model. This is my untuned model. We can see that the feature importance between those two, the tuned and untuned, is very, very different. This actually does tell me something about rank, whereas this would suggest they're all somewhat equally ranked. So a few main take-home points in the last minute. So the most of these feature importance measures capitalize on information captured from the model. But there are general approaches that could be applied to any of these. So we could use recursive feature elimination for any of these, that idea of removing one predictor at a time based on how well it predicts. Those LEC type plots where you fix all of the predictors at one value and allow one of the predictors to vary. You can in theory do that for any of the models. It's only been reported consistently for artificial neural networks, but there is something similar that's been reported for support vector machines. It certainly seems applicable to ensembles. And the permutation-based importance measure, where I take a predictor and I permute the predictor and then look at how well I predicted with the predictor as it was versus after permutation could be applied to any of these approaches. And this is an active body of research in the statistical and machine learning literature. So this is an overview of like things that have been around for a while. Last but not least, if you were interested in fitting such things, there are lots of R packages that are out there and available, and that was what was used for this presentation. So NNet and NeuralNet, RSNNS and NeuralNet tools will fit neural network models and feed-forward neural network models and provide some of these visualization techniques to fit classification regression trees. The RPart, Party, and Tree packages are all very useful. Party produces the prettiest pictures. Boosting, there's AdaBag, and Fast AdaBoost that are available. Random Forest is fit using the Random Forest package, although there's also, the Party package will also fit Random Forest, but the conditional version to address that issue with bias of continuous over categorical predictors. SVMs, the two packages that are available are the E1071 package, which came out first, and the KernLab package, which has a little bit more functionality but can be more difficult to work with. And then in general, there's a package called Carrot that sort of supplies all of these approaches to you and has some helpful guidelines and information that goes with it. So I know it's a lot. I do thank you all for attending and invite any questions, which it's, like I said, it's a hard talk to give in an hour. Claudine, you're muted. And Claudine is the only one I can see, by the way, for anybody that might be saying something. Do I need to stop presenting? Let's try end slideshow. Does that make it so that you can talk? Can't tell if people can't ask questions or if it's just that nobody's asking.
Everyone should be able to ask questions. Claudine, we can't hear your audio.
Yeah, Claudine's the only one I can hear. So I hear you. So clearly that piece is working. But like I said, this talk is a lot of information in relatively short order. So I know it's a bit overwhelming, but.
Hi, Dr. Wolf. Can you hear me?
I can hear you, yes. I just can't hear Claudine.
So thank you so much for the talk. It was great. I really enjoyed it. I was wondering, the context of the problem and the type of data that we have and the outcomes that we want to predict, does that have an impact on what algorithm we choose, or like, is there any
guidance for that? So yeah. It's not really, and in fact, that's sort of an active area that I'm looking at, because if you go into places where people have done comparisons of the different machine learning algorithms in terms of how they fit, what they end up showing, so there is some literature that says that off the shelf, with limited tuning, random forest is one of the better performers. So support vector machines and neural networks tend to require substantially more tuning. CART doesn't require as much tuning, but I would say CART is not a good choice because it doesn't tend to predict all that well or generalize well. That said, there are certainly applications. If support vector machines and neural nets are tuned properly, they can be shown to outperform. I will also say with neural networks, the newer versions, so the deep neural networks and the convolutional neural networks tend to outperform the original feed-forward neural networks that are out there. Unfortunately, there's fewer visualization tools, and so people are, I think, even more hesitant because you start getting back into the idea of being really, really black box, which is a big hesitation people have with support vector machines. At least neural networks, they can visualize, like, okay, I can at least see the connections between the input, the predictors and the hidden layer and the outputs. When you get into convolutional networks, you lose that piece to some degree. And Dr. Obey does some work with convolutional networks. I can't tell if he's still on, but he might be able to comment on that. So, it's worth applying several different approaches, but making sure that you're tuning them, because I have certainly found there are instances where random forest does the best. I'll find other instances. Neural networks, so feed-forward neural networks don't tend to win in the data that I have, but support vector machines and random forest tend to do relatively well. The other thing I would say is oftentimes it's worth comparing them to a regression approach, because regression often does as well and is easier to understand. Surprisingly well. Despite the fact that we're fairly certain that not most relationships aren't necessarily linear. And that does seem to hold in a lot of data. Now, that said, if you have one of the things I didn't talk about today, so the machine learning approaches I would think about being more in regression is sort of these variable selection approaches. So the penalized regressions, the lassos and the elastic nets that allow you to take a very large set of features and apply regression, and it sort of picks the best ones, even when there's collinearity and things like that that are often an issue for regression. So there are adaptations to regression that have made it even more viable. But again, it just sort of depends. If your goal truly is the best prediction model, it's worth comparing several different models.
And if you want to compare them, like I understand that there are parameters that can show us that whether the model is performing well, but if you want to compare if I want to compare neural networks with support vector machines, is there a parameter that I can compare, or is it just I see this parameter shows that this model is performing well and that model is performing well, but how do I compare the two? Because there are two different.
Right, so if it's talking about prediction, then you're looking at some measure of discrimination. So you could look at classification error, you could look at area under the curve, and generally wanting to do it with some sort of, I could do a whole nother tech talk on building prediction models and the idea behind that. So is splitting it into test and training. So you want to be able to validate that the model is doing well on new data that wasn't used in constructing the model. And that's the other piece of this that doesn't come into play in what I'm talking about today.
Mm-hmm.
So, but the comparison is usually just things that we would get. So classification error, area under the curve. If you're talking about regression models, it'd be looking at things like mean square error. So you can get all of those out of these machine learning models as well. You can get that same information. And so that allows you sort of this head-to-head statistical comparison between different approaches. Does that help?
Yes, absolutely. Okay. Thank you.
Can you hear me now?
Yes.
Okay, good. I had to log off and log in back. So thank you again. I just wanted to say this was a fascinating presentation and I learned a lot. So thank you.
And support vector machines we just had to gloss over all that.
Right. And we are going to take you up on having another tech talk. So, any other questions for Dr. Wolf?
So I have a quick question. So some of the clinical project that we do, though we call big data, that it's not very big. So is there any guidance on, how big the data need to be for these approaches?
So it's interesting you asked that question, and I'm speaking from a standpoint of having been an advocate that this can handle smaller data than a regression model typically could, but I have had other statisticians and informaticians argue back that they think that it's the other way around. So this goes back to what I was saying in response to the last question. I almost feel like you need to compare the different approaches. We all know that, people hand me small data sets. So if I get a data set that has 50 observations and I have 100 predictors, I'm not sure that I believe that any model can do all that great of a job. So part of it has to do with how well do you think you can actually, how generalizable do you think the model actually can be based on a small data set? So again, I've seen literature that says machine learning methods do a better job with small data than regression methods. I have seen what's the word I'm looking for here? A contradictory paper that says the other thing. And I've had arguments with reviewers on these points. So I don't know that I have a good answer to that. I feel like that's still an active area that people are trying to understand. Because in truth, I think we're all aware the rate at which we're collecting data is outpacing our ability to manage, handle, and analyze that data. So having, gene expression data on 100,000 genes and having, 50 clinical lab values and having spatial correlation, it starts to get crazy. So this is why this is such an active area of research, because I think people are trying to grapple with how do you do this and what's really valid. Again, I always lean towards, if the data set's really small, even if I get a really good prediction model out of it with an internal validation, I still have a hard time trusting it. So going back to that idea of, if I build a model off of 50 people, a patient population, do I really believe that that's actually representative of that patient population? So it might predict really well, but whether I trust it. And that's kind of the conversation to have with the clinical person that you're working with is, okay, just stop and think for a minute. Do you really believe a prediction model developed based on 50 patients?
That's a very good point. That are issues that we always face. So,
Indeed. People love to hand me small data sets.
Maybe you should give us a tech talk about how to handle all data sets.
It mostly has to do with the back-end conversation.
Right. Exactly. Any other questions? Well, thank you so much, Beth.
Yeah, well, thank you all for attending.
Thanks again.
So,
Bye.
And
Bye, everyone.